Hey guys, how you doing? This is Coach Scott with Purple Wave Chemistry. Let's go on to Unit 3 and talk about, get ready for our test. Let's start talking about effective nuclear charge and what it means and, how it affects periodic trends. So, we know some things. We've known them for a while. We know that opposite charges attract. You got a positive and negative charge, like a magnet. We also know that like charges repel. All right. Valence electrons, they don't like those inner electrons, so they're going to be going out. So we know that valence electrons are going to be attracted to the protons, but they're going to be repelled by the inner electrons. All right. So let's look at a good Bohr model. Let's look at neons. Neon, it's got two inner electrons right here. So these guys here in the outer shell are going to be repelled a little bit by those inner electrons, but they're going to be attracted by those protons. All right. So these are the valence electrons. These are the protons in the nucleus, and these are the inner shell electrons. So when we start talking about multiple electron atoms, we know that electrons are both attracted and repelled by the subatomic particles, the other ones, right? So the nuclear charge that the electron experiences depends on two factors. All right. The valence electron of like sodium, there's one valence electron, one outer electron, is attracted to the positive nucleus, the 11 protons in there, but it's also repelled by the 10 negative inner electrons. All right. So the charge acting on the valence electron is not a total of 11 protons, it's 1 because it's being repelled by the 10 inner electrons. So it's got a charge of +1 on it. All right. So those inner shell electrons keep the valence electron from feeling the full force of all those positive protons. So these are what we call the shielding electrons. Okay? The shielding electrons. So we got a little formula for this, for what we call the effective nuclear charge, or the Zeff. All right. So what the effective nuclear charge is, the amount of charge that valence electrons actually feel. The formula for it is Zeff equals Z minus S. Z is the atomic number, also known as the number of protons. S is the shielding constant, or the number of the inner electrons that shield the valence electrons from the protons in the nucleus. So if you look at sodium, sodium has a atomic number of 11. It's got 10 inner electrons, so for sodium, the Zeff, or the effective nuclear charge, would be +1. Now let's look at some in our periodic table here, right? Let's look at beryllium, boron, and carbon. They're right there in the same period on row 2, period 2 of the periodic table. Now, by looking at the shielding constant, beryllium has 2 inner electrons, boron has 2 inner electrons, and carbon has 2 inner electrons. So, the outer electrons are a little different. Beryllium, notice they have the same inner shielding electrons. Beryllium has 2 valence electrons. Its atomic number is 4. The shielding number is 2. 4 times 2 is 2. Boron has 3 valence electrons. Carbon has 4. So beryllium has a Zeff of 2. Boron has a Zeff of 3. And carbon has a Zeff of 4. Now, what happens? So what does that mean on the valence electrons? That means that these positive charges increase as the atomic number increases. Right? The shielding constant is the same, since they all have the same inner electrons. So the valence electrons get attracted to the nucleus with the greater force, and that would be carbon in this instance. So here's what's cool. It's something we call Coulomb's law. All right, Coulomb's law states, see if I can write on here. I cannot. All right, can I write? Pen. Perfect. All right, so the force, and you don't have to calculate any of this. We call it Coulombic force, and K is a constant, so we're not going to worry about it, is equal to the charge Q1 times Q2 over the distance squared between two objects. And what makes this so cool, all right, is there's a numerator and a denominator. The numerator, all right, is controlled by the Zeff on the same period. The R square controls the force as another layer is added to the valence electrons. Okay, we'll talk more about it. So look at hydrogen. 1 proton, 0 electrons, Zeff is 1. So the Coulombic force is going to be, well, E squared, or 1. If you look at helium, 0 inner electrons, 2 outer electrons, 2 valence, or atomic number of 2. So the Zeff is 2. So that means that the valence electron of helium is getting 2 times the force that hydrogen is on its valence electrons. So you got 2 positive protons, 2 negative electrons. What's going on? They're going to be coming really close together, right? So helium has 2 times the force. So how do you think that would happen to the radius, the size of those atoms? Hydrogen, 1 times the force. Helium, 2 times the force. Helium should be smaller, and it is, right? Helium is going to be smaller because those outer electrons are being pulled closer to the nucleus, right? So helium will have a smaller size than hydrogen. Lithium, okay, so now, all right, it has 2 inner electrons, atomic number of 3, so 3 minus 2 is 1, so the Zeff is 1. So this has 1 times the, it has a Zeff of 1, rather. So, looking at this, compare it to hydrogen, both of them have a Zeff of 1, but what's the difference? The difference is in the denominator, right? The denominator, lithium is got a, there's more distance between the valence electrons and the positive nucleus. So the force is what? Less. It's the denominator squared less, right? So how would this affect the size of the atoms? Lithium is going to be larger than hydrogen, right? Because those valence electrons are further away than hydrogen. So there's an electrical force that acts on these valence electrons, and it would be the same if they were the same distance for the nucleus, but they're not. Lithium has got a higher energy level, so they're further away. All right, makes sense. So this will reduce the electrical attraction of the nucleus on that valence electrons. So atoms in a group, all right, that go down that group, they're getting in a higher period, they are larger than the ones in a smaller period. So look at beryllium. It's next to lithium. It's got an atomic number of 4, 2 inner electrons. Zeff is 2. Okay, you got a force of 2 times than lithium. Let's compare this to what? We're going to compare it to lithium. So force, there's the same distance of valence electrons are. So what would be have more force on the valence pulling it in? Beryllium. Beryllium would be smaller because it's the positive nucleus are sucking in on those valence electrons. It'll get smaller. Wow. So because they're on the same energy level, shielding is the same, all right? The distance is the same, but beryllium will be smaller because of that higher electrostatic pull from the positive nucleus. And let's pause right there. So let's talk a little bit about periodic trends. Now we understand Coulomb's law, all right, and the effect the electrostatic charges that are acting on the atom. So there are four main trends that we're going to study, and I want you to know about, okay, uh, in this class. One's atomic radius, and we've already started to talk about that. Electronegativity is the other one, ionization energy, and the metallic character of an atom. So these are all shaped by these interactions, all right, again, between the positive charge of the nucleus, the negative charge of the inner electrons, the shielding electrons, and the negative charge of the outer electrons. So, let's look at these trends on atomic radius. All right, as the orbitals increase right at the higher energy level, it would suggest that the atomic size would increase as the period increases or it goes down. All right. So as you get a higher effective nuclear charge or Zeff, as you move from left to right across a period, you should expect atomic size to decrease when you go from left to right. And this is what we see. All right. So hydrogen, helium. Helium's got a little bit smaller nucleus. Lithium, as you go across to neon, starts at 152 to 58. Wow. Let's look at lithium going down. Wow. Every one as you go down increases in size. Cesium, which is at the very bottom left of the periodic table, very much large. Helium, very small. Neon, also pretty small. Again, as you add another layer, okay, size increases. As you increase the Zeff, the atomic charge, um, on the valence electrons, then size decreases because the force gets bigger. Now, let's look at our next trend, ionization energy. So, this is the amount of energy required to uh, lose an electron by an atom, right? So if you have a neutral atom, there's an equal number of protons and electrons. So you got magnesium, it's got 12 protons. It's neutral, it's going to have 12 electrons, okay? So it has a zero net charge. Now, when you add some energy, the amount of energy that is required to remove that electron, we call that the ionization energy. So when that, and really it'd be one of these electrons, when magnesium loses an electron, okay, or one is removed from magnesium, it is no longer an element. It is now, or an atom, it is now an ion with a positive charge. We call it a cation. So it's got 11 electrons, 12 protons, so it has a net charge of +1. So the first ionization energy, okay, is the energy required to remove the first electron. The second ionization energy is the amount of energy required to remove the second electron. And these are all messed up, but I've driven them on the board enough. Okay. So let's look at Coulomb's law and compare it to ionization energy. Lithium and beryllium. Lithium has a atomic number of 3, has a Zeff of 1. Okay, and its valence electron is on the second level. Beryllium has a valence or a Zeff of 2. Right? It's holding. There's more force holding that valence electrons, which is on the same level as lithium. So which of these electrons are being held closer by which element? Well, lithium's holding It's only got a force of 1. Beryllium has a force of 2 acting on the valence electron. So beryllium is holding that electron a little tighter, right? So there would be, since it's holding it tighter, it's going to take more energy to take an electron away from beryllium, okay? So as your electrical force, or Zeff, increases as we move across the periodic table, the electrons will hold those electrons tighter. So the energy required to create that into a cation or an ion is going to increase. So ionization energy increases from left to right across the table, which is an inverse of atomic radius, which decreases from left to right. Now, um, so again, it's an inverse. Now, you're going to increase the distance going down. As the distance increases, what happens to the force? It decreases. So as you go down, ionization energy will decrease. Will decrease. Okay, which is again the inverse of atomic radius. So as the atomic radius increases when you move down the table, and decreases when you move to the right, left to right. Ionization energy decreases when you move down the table because it gets further away, easier to lose the electron, and increases from left to right. So if you look at our trends at magnesium, aluminum, and silicon, they're all on the same row. Okay, so that's got a Zeff of 2, aluminum has a Zeff of 3, silicon a Zeff of 4. So silicon is going to hold its ions, or its electrons, a little tighter than aluminum. Aluminum is going to hold them a little tighter than magnesium. And you can see right here on this 3D chart, well, it actually works. So as you go across the period, Zeff increases, which makes the ionization energy increase also. And as you go down, ionization energy decreases, making it easier to grab that electron. Now, as you keep taking an electron away, well, your energy is going to increase, right? And that's the second ionization energy. And you can have as many ionization energies as you need to get rid of all those electrons. Will they happen? Probably not very easily. Well, not very easily. So when you move all those valence electrons and you have a full p shell, then the ionization energy becomes incredibly large. We studied that. The next trend is electronegativity, and that is the ability of an atom to steal an electron from another atom. So if we use Coulomb's law, the atom with the higher attractive force, okay, will have a higher attractive force for other electrons. So if you look at boron, carbon, and nitrogen, let's think about it. So nitrogen has got a higher Zeff, it's got a Zeff of 5 compared to carbon's, which is 4. Boron is 3. Nitrogen is going to grab an electron a whole lot easier than carbon will. All right. So these are pretty much going to be on the same equivalent, if you would, ionization energy. So electronegativity will decrease when you move from top to the bottom of the periodic table. It increases when you move from left to right across it. So there is some exceptions, right? The exception is the noble gases have no electronegativity, none. All right. But if you look over here, as you go across the table, electronegativity increases. As you go down, electronegativity decreases. All right. See the trend. So, and I gave you this little sign, but we're not going to worry too much about the electronegativities of transition metals, but they are there. Again, here's the exception. Um, Noble gases will have no electronegativity. None. Still haven't. So let's talk real quick about metallic character. Metals like to live in a sea of electrons. So they like to give up electrons. They're able to have them free to move about. They're not really tightly bound to anybody. So when we say metallic character, we're looking for how easy is it to give up an electron. So metallic character will increase going right to left. It decreases going left to right. Metallic character increases going down, top to bottom. All right. Metallic character increases going top to bottom. So I always like, how close am I to like helium? How close am I to cesium? If you're close to cesium, you're more metallic. If you're close up here, then you're less metallic. So here's a summary. Okay, as you move down, atomic radius increases, ionization energy decreases, electronegativity decreases, metallic character increases. As you go left to right, atomic radius decreases, uh, ionization energy increases, electronegativity increases, metallic character decreases. So you can see a pattern there. Okay, guys, so this is Coach Scott. That's Unit 3. And I think you guys will do very well on any type of assessment we have. Again, this is Coach Scott saying, Hallelujah, connect, connect.